Hello, I'm Paul Beckwith. We're well past the time where slashing fossil fuel emissions is going to stabilize the climate. We need to do that. We absolutely must do that as quickly as possible, but it's not sufficient. We've changed the chemistry of our atmospheres and oceans with our fossil fuel emissions so much that the CO2 levels have built up so high, slashing fossil fuel emissions doesn't remove the CO2 from the atmosphere fast enough. We have to deploy carbon dioxide removal methods to open up the drain, if you like, increase the sinks and pull CO2 out of the atmosphere. To see how bad our climate system is, and to see me discuss many things about our climate emergency, Google paulbeckwith.net and have a look at my website. I've talked in some previous videos about different carbon dioxide removal methods, also about solar radiation management, and I've said that iron fertilization or ocean fertilization techniques are the best chance to pull vast, huge amounts of CO2 out of the atmosphere quickly on the time scale of a decade or two to restore climate stability. So I'm going to talk about the details of this technique, what we mean by it, what work has been done thus far on it, and where we can go from here. So the general term is ocean fertilization. Ocean fertilization or ocean nourishment is a type of climate engineering that's based on we introduce nutrients to the upper ocean to increase marine food production and to remove carbon dioxide from the atmosphere. It also removes it from the ocean. There's a number of techniques, including fertilization by iron, by urea, and by phosphorus. Okay, so I'll talk about some history of different experiments that have been done, rationale, approaches, etc., etc. I should remind you, there's a lot of people that are against this type of thing. Okay, what they don't realize is how serious climate change is. Because when you understand how bad climate change is, when you understand the depths to which our oceans have been damaged by climate change and by humanity from overfishing and all of these other things, you will realize that we're in an emergency situation. And when one is in an emergency situation, one has to respond accordingly. So the first step is for people around the globe to recognize that we're in a global climate change emergency. That is coming as we get more and more extreme weather events, but we're clearly not there yet as a society. Okay, when people have their backs up against the walls, when people get extremely concerned and worried, the public I'm talking about, then they'll force the politicians and countries to act. And when countries act, I'm telling you, this is one of the major things that humanity will use in its toolbox to remove CO2 from the atmosphere and ocean system to address ocean acidification problem and abrupt climate change issue. The sooner we do this, the better. The less grief there'll be, the less hardship there'll be to human civilizations. So we're not talking about rocket science here. What we're talking about is, you know, we've destroyed the oceans. We've lost half of the phytoplankton, 40 to 50% of the phytoplankton in the last 4 or 5 decades in the oceans. This phytoplankton is not producing oxygen that we breathe, so oxygen levels are being affected. It's not pulling out CO2 from the atmosphere like it did before because there's only half of it there. So CO2 levels in the atmosphere and ocean system are skyrocketing from our emissions and also from our destruction of sinks on the planet. So history goes back to this guy John Martin, Moss Landing Marine Laboratories. Low levels of phytoplankton. Why are there low levels of phytoplankton in vast regions of the ocean? Phytoplankton, they need light. That's why they grow at the surface. They need CO2. There's lots of it. They need nutrients. Nutrients can be divided into macronutrients, things like nitrogen and phosphorus, and micronutrients, trace elements like iron. So he hypothesized that areas that were low in iron would be low in phytoplankton. So he used samples of clean water from Antarctica, added iron, and the phytoplankton grew much faster in the samples with iron than in the untreated samples. Okay, so this led to Iron X1, a large field experiment. 445 kilograms of iron was added to a patch of ocean near the Galapagos Islands. Phytoplankton levels increased 3 times in the experimental area. Very successful. So the phytoplankton is growing, it's extracting CO2 from the atmosphere, and it's producing oxygen. Okay, so other proposals to remove CO2 from the atmosphere were looked at. In 2000 and 2004, iron sulfate. If you just dump iron in the ocean, it's going to sink. If you put iron into powders like iron sulfates, and then you put it in, it's going to float at the surface for a longer period of time. It's going to release more iron to the surface, causing more stimulation of phytoplankton growth. 10 to 20% of, so it caused algal blooms. 20% of these blooms, 10 to 20% of the algal bloom died and sank to the sea floor. If it sinks to the sea floor, then that carbon is removed from the system. It goes into the sediment. So it's not in the atmosphere, it's not in the ocean, it goes into the sediments. Okay, this US company called Planktos, they were going to do 6 iron fertilization cruises from 2007 to 2009. They would have put in 100 tons of iron over 100 kilometer by 100 kilometer, which is 10,000 square kilometer area of ocean. They're shipped the Weatherbird. They couldn't provision at the port in the Canary Islands. The experiments weren't carried off. They were stopped. Okay, the Germans did this experiment to study fertilization in the South Atlantic in cooperation with India. So they deposited 6 tons of ferrous sulfate, iron sulfate, in an area of 300 square kilometers. Okay, they thought the material would distribute in the upper 15 meters, or about 50 feet of water, and trigger the algal bloom. Okay, and that lots of the CO2 that was dissolved in the seawater would then be caught up in generating the biomass, the phytoplankton algae, and then when it died, it would sink to the ocean floor. So they halted the experiment because environmentalists thought it would damage marine plants. Others said that there were long-term effects that wouldn't be seen, so they scrapped that experiment. Okay, 2012, iron fertilization iron fertilizer was deposited near Antarctica in an eddy. Now in the Southern Ocean, there's not a lot of iron. A lot of areas of the Southern Ocean are deficient in iron. So this was again near Antarctica. There was an algae bloom. A lot of carbon went into the deep ocean. Because it was an eddy, it naturally spread the iron around, and it was a self-contained system. Okay, so things that were, there are other nutrients in the water. When you put in the iron, you get the algae growth, and then it sucks out all of the other nutrients. So they measured the decline in those nutrients as the algae was growing. And there was an increase in the chlorophyll in the algae. And the particulate matter sank down. Each iron atom converted at least 13,000 carbon atoms into algae. And at least half of the organic matter sank below 1,000 meters, where it would be sequestered. Now this is the big project. This is a big project off Canada, the Russell Gorge project. The Haida Salmon Restoration Company was formed, and it dispersed 100 short tons, 91 long tons of iron sulfate dust into the Pacific, several hundred miles west of Haida Gwaii off Vancouver. $2.5 million project financed by the Old Masset Village Council on Haida Gwaii. The iron deficient waters would produce more phytoplankton that would turn that would be like a pasture, basically, and feed salmon, and you could sell carbon offsets to recover the cost and so on. Lots and lots of people were against it. Okay, 100 tons is negligible compared to what naturally enters the ocean. Think of what enters the ocean from runoff from rivers, from dust that's blown from deserts that's high in iron, from volcanic eruptions where the ash is deposited into the ocean. I mean, this is a drop in the bucket. This is nothing. Environmentalists were completely against this, a blatant violation of international law. What happened is that in 2013, the salmon runs were expected to be 50 million fish. And there was 226 million fish over, you know, look at that. Like, that's ridiculous. That's like 4.5 times the number of fish because the phytoplankton bloom developed. The little fish that were spawning managed to eat the phytoplankton, and huge numbers of them that ran in the salmon run that year. The number was very high the year after, and the year after, I believed. Lots of data was taken from this. There were satellite images of the bloom, etc. Their headquarters was raided, and all of their books and stuff were taken from their offices in Vancouver. There's a lot of, if you want a good spy story, there's a lot of intrigue in what happened in that experiment. So delve into the details. So this is how CO2 gets sequestered into the ocean. We have CO2 in, it can be in inorganic or anorganic, so non-organic form, and it can just get dissolved in the water and be pulled down and go into the carbonates in the seafloor sediment. It can be ingested by organic material, like making up plants and things, eaten by animals, pooped out, or the dead carcasses can go down. You get the organic carbon trapped in the sediment. You can also get the carbon CO2 that's dissolved in the water being carried around, being cycled around. Downwelling can bring it down, upwelling can bring it to the surface. When the ocean is cooler, you can get more of it absorbed into the seawater. Okay, and you get these carbonates on the seafloor. Once you get it, the idea is to get it out of the atmosphere, ocean system, into the sediments where it's stored for a long period of time. Okay, there's also, so the nutrients are what limits it. The reason why a lot of the oceans in the Caribbean are that really, really light blue color, you know, like a clean toilet bowl cleaner color. You know, that crystal clear, it's because the water's crystal clear. There's no phytoplankton in it. There's very little plankton in it, so it's crystal clear. The sun can penetrate deep down. It takes on that color. Okay, lots of the ocean is that way. It's basically a desert it doesn't have a lot of sea life at the surface because it's lacking nutrients, either the macronutrients or the micronutrients. There's lots of areas that are actually high in macronutrients, but low in the micronutrients like iron and zinc. So seeding with iron, the limiting factor, can stimulate these phytoplankton bloom. It's the cheapest way to suck huge amounts of CO2 out of the atmosphere. Now we can talk about, there's a couple different pumps. There's a solubility pump. Colder water absorbs more CO2. If that water downwells, it brings carbon deeper down into the oceans. The biological pump is the phytoplankton forming, being eaten by zooplankton and fish and so on. The excrement of the sea life drops to the, sinks down to the sediment, or they die, and the organic material sinks down before it's consumed by some other fish or ingested. And the idea is to get the CO2 in some form into the sediments. Okay, so this fertilization offers the prospect it can reduce the atmospheric greenhouse gases, it can reduce the amount of CO2 in the oceans, which causes acidification, and you can get greatly increased fish stocks because you increase the primary production, which is the production of, so this is primary production. It's where you get the phytoplankton growing. Okay, so ocean fertilization is a huge thing that we need to do to suck CO2 out of the atmosphere. Thank you.